Try to be super patient with me and with yourself on the last two videos this week, because it's really a culmination of a lot of the other videos that we've talked about. So hopefully you've watched those other videos, otherwise this is going to be way too much too fast. The first thing we're going to do is apply the rational zero theorem. So the rational zero theorem tells us that if we have a polynomial that has integer coefficients, which just means nice positive or negative whole numbers, then if a rational, meaning not imaginary, rational zero exists, then it must be in the form p over q, where p are factors of the constant term, that's the guy down here, and q are factors of the leading coefficient, that's the first one. So let's look at this together. Here is a polynomial. I want to determine if I have some rational zeros, what are the possibilities? And then I'm going to talk to you about why this is important. This is P, this is Q. So what I want to do is I want to look at P and say what numbers make up P. Well, 1 goes into P, 3 goes into P, 5 goes into P, and 15. So 1 times 15, 3 times 5, those are the only factors of 15, which is P. Then I'm going to look at Q, and Q is 4, which means 1 times 4 or 2 times 2. So 1, 2, and 4 are my factors. So all of the possible rational zeros for this would include any fractions that I can make using P and Q. So I'm going to say my possibilities are 1 over 1, and these can be positive or negative. So I'm using 1 over 1, 1 over 2, and again 1 over 1 I can just write it as 1, so there's no reason to write it as a fraction if it's not, and 1 over 4, so plus or minus 1 over 4. What else? Well, now I can do the same with 3. 3 over 1, which is just 3, 3 over 2, which is 3 halves, and 3 over 4. Now I'm going to do the same thing for 5. 5 over 1, which is just 5. 5 over 2. 5 over 4. And then I do the same thing with 15. 15 over 1. 15 over 2. And 15 over 4. So the good news is these are the only numbers that will work. The bad news is that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 total possibilities, because it's plus and minus for each one. So again, good news because it's not an infinite number of possibilities, but bad news is 24 possibilities kind of sucks a little bit, because that means I might be using the remainder theorem 24 times, probably not that many, but several times to come up with one where I actually get a remainder of 0 and I can do the factorization. So on the next one, we're actually going to do the factorization and use the rational zero theorem to help us to determine what we should use. Scratch that, I lied. First I want you to come up with the rational zeros, and then we'll do a question where we actually use them. So go ahead and press pause, come up with all the possible rational zeros, and then press play to see how you did. So again, P is 8, Q is negative 4. Factors of P include 1 and 2 and 4 and 8. Factors of Q include 1 and 2 and 4. So all of my possibilities would be positives and negatives of P divided by Q, which is 1 over 1, or plus or minus 1. 1 over 2, which is plus or minus 1/2. 1 over 4, which is plus or minus 1/4. So I've used 1. Now use 2 with everything in Q. So 2 over 1 is 2. 2 over 2 actually reduces to 1, and I've already gotten 1 written down, so I don't have to write it again. And then 2 over 4 actually reduces to 1/2, which I already have written down, so I don't have to write it again. Then I look at 4. 4 over 1 is plus or minus 4. 4 over 2 would be 2, but I already have 2 written down, so I don't have to worry about it. And then 4 over 4 actually reduces to 1, and I already have 1 written down, so I don't have to worry about it. Move on to 8. 8 over 1, which is plus or minus 8. 8 over 2 reduces to 4. I already have that one. 8 over 4 reduces to 2. I already have that one. So all of my possibilities in this case are right here. And again, this one's a little nicer because we have 2, 4, 6, 8, 10, 12 options instead of 24, which would make it a lot faster for me to actually solve this. Let's take our time and go through this question together. And I've tried to make it somewhat easy so we're not spending 30 minutes on one question, but this is going to be a lengthier process. The first thing I'm going to do is use my PQ, my rational zero theorem, to determine what my possible zeros are. So P is 3, so I'm going to use 1 and 3. And Q is 2, again 3 came from here, 2 came from here. Q is 2, and so that's 1 and 2 are my only factors of 2. So what are my possibilities? 1 over 1, which is plus or minus 1. 1 over 2, which is plus or minus 1/2. 3 over 1, or plus or minus 3, and 3 over 2, which is plus or minus, 3/2. Now, from here, I'm going to use the remainder theorem. And remember, the remainder theorem says, hey, plug in a number, and if you get a remainder of 0, then it's a factor. So I'm just going to check using the remainder theorem. And the remainder theorem says, hey, take one of these numbers up here, and I am going to stick with a positive number. So I'm going to start by checking positive 1, which means I'm going to take f of 1, and again, you can do this in your calculator, and I'm not going to show all of the work on that because I only have so much room on the slide to show work, and we've got a lot of work to do. But if I plug in 1, I get 2 times 1 to the 4th, which is 2, plus 1 to the 3rd, which is 1, minus 5 times 1 squared, which is just minus 5, minus 1, plus 3. And that gives me 2 plus 1, which is 3, minus 5, which is negative 2, minus 1, which is negative 3, plus 3, which is 0. So I got super lucky, but don't think that's going to happen every time. I got lucky on my first try that 1 is a factor. But what does that exactly tell me? Well, that means I'm going to use synthetic division using 1, and I'm going to write the 2, and then that's x to the 4th, 1x to the 3rd, negative 5x squared, negative 1x, 3. Leave a line, leave a space for your remainder, but keep in mind this remainder should be 0 based on the fact that this is 0. So if it's not 0, we did something wrong. So let's use synthetic division. Bring down the 2. Take 1 times 2 to get 2. 1 plus 2 is 3. 1 times 3 is 3. 5 plus 3 is negative 2. Sorry, negative 5 plus 3 is negative 2. 1 times negative 2 is negative 2. Add those together to get negative 3. 1 times negative 3 is negative 3. Remainder is 0. So perfect. What this means is I am now left with a factor of x minus 1, because remember we tried positive 1, so it's x minus that, and 2x, 1 less than this, is cubed, plus 3x squared minus 2x minus 3. So again, that came from 2, 3, negative 2, negative 3. Now from here, you can either, you have a choice, you can either look at another rational, so I could try negative 1 and see if that worked. I could try positive 1/2 or negative 1/2, etc., etc. I could try any of those, or once I get it to the point where I can factor it using a method I already know, I could also do it that way. So that's what I'm going to choose to do, is I already know that x minus 1 is a factor, and what I want to do is I want to look at this, and if we look at this, I can see based on the numbers that I'm going to be able to factor this by grouping. So if I look at this and this with the minus in between, I'm probably going to factor this and not have to do any more with the rational zero theorem. So my factorization already has my x minus 1 because I can't lose it. And then I'm going to look at this factorization. Let's put this in brackets to kind of keep it all separate. 2x cubed minus 3x squared. I'm going to take an x squared out of both of those, leaving me with 2x plus 3. I'm going to put my minus in the middle. Nothing comes out of 2x and 3 except for 1, but it's a minus 1. So that changes minus 2x to positive 2x and minus 3 to positive 3. So if you'll notice, this does factor by grouping. So I have x minus 1. The stuff on the inside turned into 2x plus 3 and x squared minus 1. Hopefully we can see that x squared minus 1, I'm going to just recopy this. X squared minus 1 factors, because it's a difference of squares pattern, into x plus 1, x minus 1. So what's my final answer? Well, it looks like I got two of these guys, so it's x minus 1 squared, 2x plus 3, and x plus 1. Now, keep in mind, the question didn't say factor this. It says find the zeros and their multiplicities. So I had to factor to get there. But remember, this is 0 equals this, because that's essentially what I did, is set 0 equal to that. So to find my zeros, I'm going to take x minus 1 and set it equal to 0 to get x equals 1, multiplicity of 2. And then 2x plus 3 equal to 0, which means 2x is negative 3. X is negative 3 halves, multiplicity of 1. X plus 1 equals 0, so x is negative 1. Whoops, forgot my negative. Negative 1. So here's my answers. 1 multiplicity of 2, negative 3 halves, and negative 1. So I do have one for you to try on your own, and I tried to make it not horrible because I didn't give you a lot of options for the rational zero theorem. I would really like you to try to get at least as far as you can, even if you can't finish the problem on your own because we haven't practiced enough. That's okay. Get as far as you can. When you're done, press play to see how you did. So again, using the rational zero theorem, I would look at 5 for my p's, so that's 1 and 5, and look at 1 for my q's, so that's just 1. So that's why I said this one wasn't so bad, because my possibilities are plus or minus 1 and plus or minus 5 over 1, which reduced. So here's my options. And again, that's just giving me my rational zeros, so there could be some irrational ones. We haven't talked about that yet. But here's what I have so far, which means I'm going to do some checking using my remainder theorem, which means I'm just going to plug in, and again, start with whatever you want. If you have a feeling about one, go with it. I'm going to plug in 1. That gives me 1 cubed, which is 1, minus 2 times 1 squared, so that's just minus 2. Minus 14 times 1 is minus 14, minus 5. That's not 0. So I don't even care what it is. I just want it to be 0, and it's not. So let's try negative 1. Negative 1 cubed is negative 1. Minus 2 times 1 squared is minus 2. Minus 14 times minus 1 is plus 14. Minus 5. I add those up. It's still not 0. F of 5, because there's only 4 I can check, right? So I'm running out of options here. This one didn't work. So let's try f of 5. X cubed would be 125 minus 2 times 5 squared, so that's minus 50. Minus 14 times 5, so minus 70, and then minus 5. This one's looking promising. 125 minus 50 is 75, minus 70 is 5, 5 minus 5 is 0. Yay, we can celebrate. Now, what does that tell me I can do? That means I'm going to start with 1 x cubed, negative 2 x squared, negative 14x, and negative 5. Remember, when I divide, this should be 0, and I'm dividing by 5, which means the factor is x minus 5. That's where the 5 comes from. It's x minus 5. So how do I do it now? Bring down the 1. 5 times 1 is 5. Add those together. Multiply, add, multiply, add. So what I have now is x minus 5, which came from here, and what's left over here, which starts at x squared, one less than this. So x squared plus 3x plus 1 equals 0. That's what I have. I'm trying to find the zeros and their multiplicities. So now I'm looking at, this is a quadratic. Can I factor that quadratic? Am I able to find two numbers that multiply to 1 that add to 3? No, I'm not. So if it said factor completely, I'd be done right here. But because I have to find the zeros, I know that my zeros, one of them is x minus 5 is a factor, so x minus 5 equals 0. My 0 is 5. Again, same number as right here. The other zeros come from this, which unfortunately I'm going to have to use the quadratic formula for. So x equals the opposite of b plus or minus the square root of b squared, so 3 squared is 9, minus 4 times 1 times 1, all over 2a. So again, I'm not showing a ton of work, but we've done a lot with the quadratic formula, so you know what work should be shown. This is negative 3 on top. This is 9 minus 4 is 5. So my zeros would be 5, and also negative 3 over 2 plus radical 5 over 2, and then negative 3 over 2 minus radical 5 over 2. That would be all of my zeros. So one rational, and then these are irrational. They're not imaginary yet, but they are irrational because I've got square roots of numbers that aren't whole numbers.